presentation by Koos Doppelen, and it's a joint work with Johan Daly.
Yes. And this is, yes, okay. Thanks for the introduction. So, what I want to talk about in this talk is diffusion layers in symmetric cryptographic primitives. And as we have already had a few talks about that in the session, and basically all of them focused on a specific type of mixing layer, which is NDS matrices. So we've seen all kinds of ways to optimize them and to find lightweight NDS constructions. But they're actually not the only type of mixing layer that is used in cryptographic primitives. And in this talk I would like to focus on a construction that is used in the catch-up function, but which has not received as much attention as a type of, as a building block for cryptographic primitives. So the idea how it works, very briefly, is that you have these, every square is a 1, every red square is a 1, every white square is a 0, and the parity is computed over the columns of this cubical state. So here there's only one, so that becomes 1, 2 becomes 0. And then here there happens some linear operation that's computed on this parity, and then this is stretched and then added back to the original state. And the intuition why this might be an interesting building block is that this matrix multiplication, which is typically expensive, you now only have to compute that on a compressed part of the state. So first there is this compression, then you do some operation on this, and then this stretched back to the full state to get a lot of diffusion. And of course there is some cost involved for actually computing these parities. But the computational cost of this is only 2 XORs per bit in catch-up, which is very low. And it also, there was a paper at FSE last year, which presented very good bounds on trails against differential attacks. So the main goal of this work is to generalize this type of mixing layer and show that it can actually also be used in not only in catch-up, where you have this state that's based on bits and it's a cubical shape, but we can also actually use this on a typical rectangular state with elements of finite fields. So to do this, we look at our state as a matrix, which is given here, and we have to find some function of A that we then add back to the state. And the first thing that we want to do is to compute the parities on this matrix, and we do that by just adding this all one vector in front. So it contains of the number of rows once, and it's a row vector. And if you think about it, this basically just computes these parities if you compute this matrix product. So we call this the column parity. And then we want to do some linear operation on this column parity. And we do that by adding a different matrix after that, which we call the parity folding matrix. And that specifies what computation we're actually doing on this on these column parities. And together this is a vector, and this we call this the theta effect. So the effect caused by this mixing layer. And then of course we get a 1 by n vector, but we still need to stretch it back to the original dimensions of the matrix. And we do that by appending a column vector of all ones. And we call this the expanded theta effect. And then we can add this back to the original state. And that is then the definition of our column parity mixer, which is how we call these mixing layers. And of course these two vectors just form the R1 matrix n by n in front. So this is then the final expression that we have. And before looking at several properties of these mixing layers, there's one special case where this matrix is circular. So if the parity folding matrix is of this shape, then we can also say that this actually corresponds, we can describe this by polynomial, and we give a full description of this mixing layer in terms of polynomial arithmetic. So the computation of the effect given parity polynomial, this corresponds to a polynomial multiplication modulo 1 plus x to the n. And then we use this to give a full description for the column parity mixer, where the state is now seen as a bivariate polynomial. And well, it all works out, and if you like polynomials, then circular matrices are the way to go. So now we have this definition. So now let's look at some properties of these mixing layers. So we start by composing two column parity mixers and see what happens. And if you work this out, then we end up with this expression. And there is this square here of the all-one matrix that appears there. And this causes an interesting difference between column parity mixers on states where the number of rows is even and where it is odd. Because if it is even, then of course it becomes the all-zero matrix. So this whole term disappears. And then the composition of these column parity mixers is again a column parity mixer. And it turns out that this group formed by the set of column parity mixers on states with an even number of rows and composition is isomorphic to this additive group. And what is nice is that all of these column parity mixers are involutions actually and commutative. But if m is odd, then this term becomes a bit different. And then it turns out that if z plus the identity is a vertical, that this group becomes isomorphic to the general linear group, which are the n by n binary invertible matrices. And they're not commutative, and their inverse is actually harder to compute. So the designer can already choose whether he wants to have some primitive with an efficient inverse, or whether it's going to be used in some context where the inverse is actually not necessary. And I might go for an odd number of rows to get interesting diffusion properties. So to look at some propagation properties. So of course, if you have a difference at the input, then this is all linear. So if we input some difference, then we can also just compute this column parity mixer on this difference, and well, it's exactly what we expected. But for linear masks, if we have some matrix V at the output that specifies a linear mask, and we would propagate this back, then it turns out that the mask at the input is actually this thing, but then with the transpose of this parity folding matrix. And that is useful if you want to search for linear trails. Then it's very, very similar to searching for differential trails, but you need to take a transpose of this this parity folding matrix. So to look a bit like how does it actually work for diffusion. So imagine there's a state like this, where there are two active cells in one column. We call this thing an orbital, following previous papers. And then it turns out that if you compute the parity of this this state pattern, then theta actually acts as the identity, which is something that we need to take into account when designing something using a column parity mixer. But there are input states for which this column parity mixer actually acts as the identity. That's something that we can work around. And it turns out that all these states in what we call the kernel of the column parity mixer, they can be described as a set of orbitals. And this allows us to easily count the side dimension of this space compared to the complete space of states. And this has a consequence that the branch number is always going to be 4, assuming at least 2 rows in this matrix. And that if you would make this much larger thing, you wouldn't really get a higher branch number, because there's always this case possible where you have 2 active cells in one column, and then after theta you would also still have this, because the column parity mixer acts as the identity. So you don't really get a higher branch number, but over multiple rounds, we'll see that this actually yields very good diffusion. It also means that just having a column parity mixer and some nonlinearity is never going to be enough, because we need some transposition layer that moves bits apart. Because if an attacker can start out with a difference like this, we want to sort of guarantee that in the next round he should not be in the kernel again. He should quickly move out of this kernel. But it also means that if you would have like a single bit difference in one of these cells, then it very quickly propagates to multiple columns and over the full length of the column, so that it goes very fast. So if we would compare only these mixing layers without any context of a cipher or something, then we can only look at this XOR count that has been mentioned a few times, and the branch number as a metric for diffusion. So most of these numbers are actually from the paper that Thorsten presented earlier. And we see that MDS matrices are just a bit more expensive to implement, although the branch numbers are really good. But more recently people started dropping this requirement for MDSness of the matrix. And then we can get much cheaper matrix multiplications that still give good diffusion in multiple rounds. And if we look at where column parity mixers fit in this picture, then they're pretty close to these near MDS matrices. And it turns out that matrices that have previously been used in Midori and Minalver, we can actually also view this and define it in this way as a column parity mixer if you reorder a bit of the bits. So this matrix is used in a few ciphers, typically called near MDS. And it turns out that if you reorder the bits of like 4 bits of one column as a 2x2 matrix, then this exactly corresponds to the column parity mixer with 2 rows where this is the parity folding matrix, which is a funny correspondence between these two ways of viewing this mixing layer. So now we've looked at these building blocks, and now of course we want to use them, build some permutation with this type of mixing layer, and then it becomes clear that we can actually do this in 2 phases because of this kernel of the column parity mixer. So of course you first pick your design goals and you can choose your dimensions, where you have to make some trade-off between fast mixing or efficient implementation. You can pick some nonlinearity reasonably independently. And now we can consider truncated trails in the kernel, which is completely independent of the parity folding matrix, so we don't have to choose that yet, to already choose some transposition in there. Because that needs to be, there should not be any attack possible there anyway, so we can start by choosing this transposition independently of the column parity mixer. And then of course we can start looking for trails outside the kernel. We can determine this matrix. We add some round constants. Thanks to this crypto paper from 2017, we know how to do that now. Well, you do more analysis, determine the routes, implement it, and give the name. So now we want to look at trails, right? So a lot of papers focusing on finding differential linear trails using MILP or MLLP. But there was this paper that used a more dedicated approach for Ketchup. And they actually got very good bounds there, and we're trying to fit our design into this work and trying to reuse the method that we used there. And then we should note that if you have some R-round trail with some weight, then there's always a 1-round differential with weight at most the floor of W over R. And it was observed in this paper that there are actually less 2-round trail cores with a weight less than 2L than 1-round differentials less than L. So what we did is to sort of gain 1 round. So we didn't start by having 1-round differential and extending that. But we started with generating these 2-round trails and extending those like R-2 rounds forward and backward. And then that should contain the trail that we want to have. And then this generation of all these trail cores that is modeled as tree traversal, following this paper by Sylvia Mella, Johan Dane, and Jules Nash. Not really going into the details here, but the idea is that you can build a tree in a certain way, and using all kinds of properties of this this design, namely that there's a lot of rotations in the tree, and we can build this tree in a way that these weights increase. That allows us to do a lot of pruning in this tree, and to actually cover a larger search space than you would otherwise have to cover. An interesting difference between this work and the work that they did and presented last year is that if they would extend the trail, then their nonlinear layer, the chi step in theta, would actually cause a lot of branching of the search space for trails. But in our case, we're looking at truncated trails, so we don't have that. But the column parity mixer itself actually now causes a lot of branching if we extend these trails. And they did not have that a lot. So some interesting differences between, on the one hand, this bitwise weak alignment trail search and our truncated trail search on the strong alignment. So we wrote dedicated software based on the software they used for ciphers and permutations based on this this type of mixing layer. I should put it online. It's not online yet, but it should put it online. So what we eventually built is a permutation, 256-bit, which has dimensions 4 by 16, and every cell is 4 bits, so there are 4-bit S boxes. And a round consists of several steps, where the first is a 4-bit S box, and we chose this rotational symmetric S box given here by the first Boolean function for implementation efficiency reasons. And then for our column parity mixer, we chose a circulant parity folding matrix, where the first row is given by this. So in compared to Ketchup, then there would be 2 rows that were where you compute the parities, and you would use them to add them back. And in this case, we choose 3 rows. So that, if you start with one cell difference, then it quickly propagates to 13 on the after theta. So it goes very fast. And then experimentally, we chose some ways to reorder the bit, to shuffle them a bit. So we rotate all the rows down, and then we rotate the cells horizontally as well. And we add some round constant to weird places, because that happens to match nicely with the bitwise implementation. Not really going into details of the choice there. But if we then do analysis on this cipher, then we first started with some simple avalanche tests. So we took a random state and flipped 1 bit, and then looked at how many rounds does it take before all bits are flipped with 50% probability. This is called strict avalanche criteria, and this is already fulfilled after 3 rounds. And if we start with like only 1 bit, 1 and the rest are 0, then like all the bits are touched after 5 rounds already, which is full diffusion, which is I think is quite good. And if we really look for linear differential trails, then after 4 rounds, if you look in the kernel, then we already have at least 52 active cells. So yeah, we found the trail with the least number of active cells, so 52. And then outside the kernel, we start looking for differential trails. We already get a differential probability of 2 to the minus 92 after 4 rounds. And linear is not as good, but 2 to the minus 80. And that's only after 4 rounds. And then we looked a bit at different types of cryptanalysis, and we believe that these other things are not really a concern. So for the implementation, we implemented this on a microcontroller, which is the sort of target architecture. So 32-bit ARM microcontroller. And we designed the cipher in such a way that bitwise implementation is immediate. So this is sort of how we match all the 256 bits into 32-bit registers. And if we then we can compare this to some other ciphers, where some are really known for having really strong bounds on their differential probabilities, like AES and Ketchar, and some that are known to be very fast but have somewhat weaker bounds. Then if you compare this in this specific architecture, I'm not trying to claim that Mixifair is better than any of them, but just if you look at this specific architecture, then we think that we can get a really good trade-off between, on the one hand, still quite a decent implementation speed, but on the other hand, actually quite strong bounds on trails. And we think that this trade-off is a nice place in this design space to be at. So here we normalized a bit per round to see like what the strength of a long round is. And then we think that design based on comparative mixes can be quite complex. And maybe a way to test, but that was it. So thanks for your attention.
Actually, we're a bit late, so do we have a short question?
No, just going to say something.
Okay. I have not really a question, it's more like a comment. I find it very reminiscent of Noikion, actually.
Oh?
Noikion, the block cipher of your caller.
It might be partially inspired by previous designs, but there are definitely some differences.
Maybe a comment. So Nokia, you can also portray it as a double parity mixer. It is actually a double parity mixer.
Yes.
Yeah. Then there were some other choices.
So then let's thank Paul and all the speakers of the session again.